Hello there! In this lesson we're going to learn about carboxylic acids. These are all your organic acids like citric acid that you might find in citrus fruit, and esters, which are in all sorts of scents and flavorings that give things a specific smell or taste. And so we're going to look at all the different properties of these molecules and how they are different from the other ones we've studied so far. So carboxylic acids always have this carboxyl group attached to the rest of the molecule. Carboxyl group has a carbonyl part and a hydroxyl part. And so what you do is, to name it, you're going to use this oic acid suffix, and carboxyl groups are always the highest priority. So it doesn't matter what else is there. If you see one of these carboxyl groups, that's going to be at the end of the name. So first off, as an example, you got this cyclic aromatic compound called benzene. And so with the carboxyl group, it's now benzoic acid. There you go. We got two here on this 3-carbon molecule, so this is going to be propandioic acid because it's on both ends. This one here has two functional groups, so it's butanoic acid. And what you do is you always start counting from wherever the carboxyl group is. So there is a hydroxy group on carbon number 2. So 2-hydroxybutanoic acid. There you go, naming for carboxylic acids. So to make a carboxylic acid, you're going to need an aldehyde, so carbonyl group already on the end, and then you're going to oxidize that. So you can use one of your oxidizing agent like potassium permanganate, or you can just indicate it with like the square bracket with an oxygen. And what will happen is that you'll just add on the rest of the carboxyl group. So you leave the carbonyl group there, and then you add another oxygen in there. And so you went from propanal to propanoic acid. So our next group we're going to look at here are the esters. They're the ones that are often found in smelly compounds or flavorings or scents that are made artificially or naturally. And so they have a carboxyl group, but it's in the middle of a chain, and they're attached where the hydrogen was. So the way that it works is a condensation reaction, just like when we made the ethers. And what you're going to do is remove the water, and you're going to end up with an ester. So you have the same 3 carbons and the same double bond O, and then one of those oxygens from the 2 that were there to begin with, and then you've got 2 carbons from the alcohol side of this molecule. So there you go, you got an ester linkage that holds the 2 together, starting from an alcohol and an acid. The naming for esters is a little different. You got O8 as the suffix. That's going to show that it's an ester. And so the part that has this carbonyl group is always going to be the part that gets the O8. And so this is going to be a methyl group that is attached to this 1, 2, 3 propanoate. So this is propanoate with a methyl group on it. This one here, you see the carbonyl group is on here, so that's going to be carbon number 1, 2, 3, 4. So this is a butanoate. And we have an ethyl group on the oxygen here. Carboxylic acids and esters are both pretty polar because of the carbonyl groups that they both have. But the acids are a little more so because of the hydroxyl group, the hydrogen on the end there. So if you're comparing molecules with the similar molar mass, the one with the carboxyl group will have a much higher boiling point than the one that just has an ester linkage in it. So it is polar, definitely more so than alkane of a similar weight, but not nearly as polar as that carboxyl group. Triglycerides are the result of a unique alcohol that has 3 hydroxyl groups on it called glycerol, and a condensation reaction with 3 different acids, or fatty acids as they're sometimes called. So you do that same condensation reaction, like remove the waters, and then you end up with what's called a triglyceride, which has 3 ester linkages holding all 3 of them together there. So you end up with the 3 carbons here, and then you will have 3 ester linkages. They'll all go to the oxygen first, and then to the carbon with the carbonyl group, and then the rest of the molecule looks like 5 more carbons. So 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then, of course, hydrogen's all around, blah, 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 wherever the carbon is not up to 4. There you go. There's a triglyceride with 3 ester linkages holding it together. So those triglycerides are found in animal fats and in the oils that you can get from plants. So an example might be vegetable oil that you see in this container here. I'll need my red pen back. There we go. And you notice that it's liquid, right? And but if you buy margarine, which is processed vegetable oil, you'll notice that it's a solid under pretty much the same conditions. So the difference is whether or not the fatty acids are saturated or not. So if you recall from earlier, saturated means no double or triple bonds. That means has the maximum number of hydrogens. So this guy here is saturated, and so it'll have a higher melting and boiling point. And this one here is unsaturated because of the double bonds, right? And it'll have a much lower melting and boiling point because these molecules can't snug up to each other very well because of those double bonds that cause the fatty acids to have like an irregular shape that doesn't really stack very well. It's like taking a whole bunch of chairs that are from different dining sets and trying to stack them. They won't stack very well. And a saturated molecule is like a whole bunch of chairs from the same set, and they all stack together no problem, right? So the process of turning vegetable oil into margarine is called hydrogenation, and you add hydrogen in there, and it makes the molecules more saturated and therefore more solid, which is great if you like margarine. But there is a little drawback. Some of those fats can be changed from their cis formation, which is this guy with the carbons on the same side of the double bonds, to the trans version, right, where the carbons are on opposite sides. Well, aesthetically, it looks pretty much the same, and you wouldn't worry about it too much that way, except that it seems to be linked to cancers and heart disease more. And so these trans fats are something that we want to avoid having too much of in our diet. Our body doesn't deal with them very well. We don't have very good enzymes to break them down, and it can lead to some health issues. So check your labels and avoid the trans fats, and now you know what they look like at the molecular level. So the last reaction we're going to look at involving esters is going to be saponification. And what you do is you start with a triglyceride, one of those fats or oils from a plant or an animal, and you're going to throw in a very strong base. And the base is going to go through and snip all these bonds, and you're going to end up with the glycerol back, and you're going to have the sodium. Let's use a different color for the sodium ions, and the remainder of the molecule will be there as well. It should be an O with a negative charge, and then a carbon. There's your carboxyl group minus the hydrogen, and then of course the rest of the carbons down till you run out. The reason why these things work so well as soaps is because this whole end here is all non-polar, and it will be attracted to dirt and oils, right? And this end here is very polar, and it'll be attracted to water. So if you have like a blob of dirt, let's use a different color. Let's make my dirt black. So you get a blob of dirt, and then you throw in a bunch of these soap molecules. Well, all of the blue ends, the nonpolar sides, will stick to the oily dirt. And then all of the ionic or charged ends will be attracted to the water. And so if you get enough soap in there, this whole blob, dirt and all, will dissolve in the water and wash away. All right, there you go. Hope you learned something. See you soon.